In this video, I'm going to show you exactly how to do steel reinforcement takeoffs. We'll cover understanding the basics, the key terminology, the manual takeoff method, the ratio method. We'll do an example and share with you our Excel template that we use, and also talk about some common mistakes. Okay, let's start off with the basics of steel reinforcement takeoffs. So starting with the big simple question, what actually is a reinforcement takeoff? Well, it's the process of quantifying all of the reinforcement required for a project or a specific activity or slab. To do this, we'll review the structural engineering drawings to determine the type of reinforcement, the size of the bars, the length, the spacing, and then produce a total quantity in tons. So why do we need to know this? Well, there's fundamentally three core reasons we'd use a steel reinforcement takeoff. First one is cost estimating. When we're preparing an estimate for the project, we'd want to know the cost of the reinforcement supply and then also the labor to install. Both of these are going to be driven by the total weight of reinforcement. When procuring, so we'd want a schedule of reinforcement that we can send to a supplier of what we want to order. Then also with construction, methodology, and planning. Quantity of reinforcement is going to impact the schedule, so the duration to complete the works, the number of crane lifts, the type of crane we're going to need, the number of deliveries, and also planning for our resourcing and labor needs. Okay, so what are the different types of steel reinforcement? Well, we've got bar reinforcement, so these would be used in slabs, beams, columns, footings, as well as starter bars. We'd have mesh, so this is where we have like SL82 or SL92 mesh, which is used in slabs and driveways. We've got fabricated items, so we can have L-bars, U-bars, or custom bends, or even prefabricated cages that we'd drop into piles. And we'd also have accessories. So these are things like bar chairs that mesh will sit on, spacers, tie wires, and other components that we'll need to order. Okay, so how do we do a steel reinforcement takeoff? Well, there's two main methodologies that we can use. There's a manual takeoff method. So this is where we perform a detailed measurement of every single bar in the slab and multiply it by the weight per meter of the bars. So for example, if we do a takeoff from a drawing and we determine there's 100 meters of N16 bar and it weighs 1.65 kilograms per meter, then the total weight would be 165 kilograms. This would be required for procurement or detailed cost estimates. The ratio method is when we want a quick and easy way to calculate the amount of steel in a slab, where we use standard ratios for different types of structures of the number of kilograms per meter cubed in a typical structure. So for example, if we have 30 meters cubed of a concrete slab, a typical ratio we'd use is 150 kilograms of steel in a meter cubed, then we can determine in that by multiplying the volume by the ratio, we get 4.5 tons of steel reinforcement. This is used for estimating and quick analysis. So what units of measurements would we be using? Well, we've got linear meters, which is used when we're ordering bars. So for example, 100 meters of N16 bar, we'd have the actual number of bars. So this is where the bars come in prefabricated lengths. So typical would be 3 or 6 meters. And then we just get the number that's up a bar. We also want to know the weight, so the kilograms or tons of total steel reinforcement, which is useful for estimating, particularly when estimating labor costs, because when we're preparing labor cost estimates for steel reinforcement, it's always done in man hours per ton, and we'd use standard bar weight formulas, so the weight per meter of an N16 bar and N24 bar. And also when we're doing steel mesh, so reinforcement mesh, we'd want to get it in meters squared. Okay, so now we understand the basics. Let's look at some of the key terminology around steel reinforcement takeoffs. Okay, so the first term you need to understand is the types of bars. You'll always see things like N16, N24, N20, so on and so forth. The N refers to normal ductility. This is a term for the type of steel. So 500 MPa yield strength means normal ductility. The number, so the number after that, when you get N12, N16, N20, refers to the diameter of the bar in millimeters. So common sizes you'll get will be N12, N16, N24, and 32. The larger bars are typically used in columns and beams where there's a big structural loading, and the smaller bars are used in slabs or ligatures. So what you typically see on a drawing is the type of bar followed by a dash with a number. That number is the spacing between the bars. So N12 200 means N12 bars at 200 millimeters spacing. So it means 12 millimeter diameter bars spaced at 200 millimeters center to center. So if you look at a drawing like the slab I've shown on screen, it says N16 150 W top, which means on the top layer of the slab running east to west, there's N16 bars and they have 150 mil spacing. This slab could have bars going in one way or it could have bars going in two ways. It depends on the plane of the drawing you're looking at. The next term you need to understand is the lap length. So where two lengths of reinforcement overlap, is remember the bars come in prefabricated sizes, maybe 6 meters or 3 meters, and the slab or the structure might be longer than that. So for example, if you have a 9 meter slab and you've got 6 meter bars, you'll need 1.5 bars. The lap length is the distance you have to leave overlapping the two bars when you install them. So this will always be on the general notes of the drawing. So for example, in the table shown on screen, you can see N12 has a 460 mil lap length. That means when you install two N12 bars, it has to overlap by 460 mils. The length depends on the diameter of the bar, the concrete strength, the bar location, whether it's used in tension or compression, and typical rules of thumb. So typical rule of thumb would be 40 to 50, the lap length will be 40 to 50 times the diameter of the bar. So for example, an N16 bar will have a 640 to an 800 mil lap length. The next term is a starter bar. So a starter bar is a vertical bar projecting from a slab footing or beam that's used to tie in the next concrete pour. When you look at the specs on the drawings, they'll detail the correct embedment length and exposure height. Now, starter bars are often missed in quantity takeoffs, so they're important to factor in the construction joints between the slabs and the additional lap lengths you'll need to allow for. Okay, the next one are ligatures, ties, or stirrups. So these are smaller diameter bars, typically N10 or N12, used to confine the main bars in columns and beams. They're usually closed loops, and there's something like 200 mil, and they'll be shown in section views, not plan views. So these take the big structural bars and they hold them in position. Okay, so fabric mesh is used in rectangular structures or slabs. Now, the common types will be SL62, 72, 82, 92, and the number at the start. So for example, in SL82, the 8 refers to the diameter of the bar used in the mesh. These steel mesh are always measured in sheets or meters squared. The next term is cover. So cover is the distance from the reinforcement to the outside of the concrete structure. It's critical for durability and fire protection, and it affects the bar placement and spacing. Cover will always be specified in the general notes of the drawings. For example, there will be something that says all cover on reinforcement needs to be 40 mil from the edge of the structure. Okay, so we understand the basics of steel reinforcement takeoffs and we know the key terminology that surrounds it. Let's now start looking at some structural drawings and talk about how to read these to determine what reinforcement is required in the structure. So the first and most important drawing are always going to be the reinforcement layout drawings. You'll typically get a plan view, so an overview of the slab like I've got on screen, which shows a 2.5 meter wide slab a 2.5 meter long slab that's almost a meter wide. These are the main layout drawings, and they show the position, spacing, and direction of the rebar. So you can see in the X direction, we've got N16 200 bars, so 16 mil bars at 200 mil spacing, and in the Y direction, we've got the same thing, N16 200 bars. So this gives you, imagine, a bird's eye view of the slab. Now, we also need to look at the section view. So a section view is like a cut through the slab, so you're looking at it from within the slab. So these cross-section views help you better understand the direction and layout of the reinforcement. So from the top, we can see it's a 2.5 meter long slab, it's 920 mil wide. Then from the section view, we can see that this slab is actually on top of another structure. The CJ note refers to a construction joint, that there's a joint between the two slabs. It helps us to better understand that in the vertical, the steel reinforcement coming out of the page, that's a starter bar from the slab below. They're around the edges, and we can see that there's a grid layout showing N16 200 in both the X and the Y direction. Now, the other type of drawing that we'll have will be detailed drawings and section views of complex structures. So this will be typically when you have cast-in elements like rag bolts or Rio cages that show connections to other structural elements. So for example, this section shows the connection of a structural slab to a steel column. So these would be used in wall-to-wall connections, beam to column elements, penetrations where you have surfaces coming through the slabs, or detailed footing drawings. Now, the last form of document, in addition to the drawings, will be a reinforcement schedule. So in some instances, you might have the reinforcement layout drawings, but you might send these to a supplier to do the scheduling. So a schedule is basically a list of all the different types of bars and the quantities that you need them in. They'll show you the bar mark, so they might give a code to all the different types of bars, the different shapes, the diameter and the lengths, the quantity per location, and the total weight. And in addition to the drawings and the schedules, you need to refer and read to the general notes. So the general notes will include things like design assumptions, probably not that important, but concrete cover requirements will be important. The lap length rules will be important, the minimum bar sizes, and placement tolerances. Okay, so now let's get into the nitty-gritty of how to do a steel reinforcement takeoff. I'm going to start by talking about the manual takeoff method. So the general process, it's pretty self-explanatory. Review the drawings and specifications, set up a quantity takeoff sheet, and I'll use a specific type of Excel document that I'll put a link in the description of the video that you can download. Measure the lengths of the bars and then multiply the weight. So what we want to calculate is the total length of all the bars used and multiply these by the weights. Okay, so I'm just going to do a really simple example of the slab we were looking at in the drawings before. So this is the quantity takeoff sheet I use for steel reinforcement. Basically, what you do is you list out all the different types of bars. You put in description, the name, the shape, the diameter, and based on this table of values, so all the different reinforcement bar types, it'll give you the weight in kilograms per meters, and we're just using a standard lap length. But yeah, so I'm using the really simple drawing from before, 2400 long slab, 920 mil wide. The T in T means there's two layers of mesh, top and bottom. Okay, in the X direction, there's 2400 long bars. They're N16 at 200 spacing. In the Y direction, there's 920 mil long N16 bars, 200 mil spacing, and there's a layer on the top and the bottom. And there's also these N16 200 L bars that come out of the slab below, the starter bars. And we also have to pay attention to these N16 200 U bars. Okay, so the first one we'll refer to is the x-axis, which is the longitudinal web. Pretty easy to get confused when you're looking at all the different section views and to either double count or miss things if you don't pay attention to which axis things are in. The 2400 long bars, we'll refer to these as the straight bars. It's N16 200. Standard unit length is 6 meters. Now, this would matter if the length of the slab was longer than the standard bar, because we'd have to factor in a lap. For example, if I had a 1 meter long bar and it was 2400, I would have to use 3 separate bars and I'd have to have a lap between them. So that only matters if the prefabricated length is shorter than the length of the slab and you have to factor in a lap. But if 6 meters is a pretty standard length, we wouldn't have a lap here, so we don't have to factor it in. Okay, so the width of the structure, the length of the structure, so the length here is 2.45, and that gives us 6 bars in the horizontal. So if you can imagine what we've worked out, in the x-axis, there's 6 2.45 meter bars in this direction, gives us a total length of 14.7 meters of N16 bar, and the weight is going to be 0.02 tons, so like 20 kilos. Let's now do the y-axis. Straight bars at N16 200. Whoop, copy that. Straight N16. Standard length is 6 meters. The width of the structure in this one is going to be the X length, so 2.45, 0.92, 200 spacing, and then copy that formula down. It's going to be 0 laps as well because it's not longer. It's going to be a total of 12.88 meters. So that covers the Y direction. Then we need to factor in these 2 U bars, which they've given a standard lap length, which we'll assume we'll go off, rather than looking at the general notes for this example, we'll just go off a standard lap length for that type of bar. And N16 200 U-bar, standard length, let's say, is 6 meters. For this one, the width of the structure will be, it's NA, it's going to be 0.92 plus twice the lap length. So if we look up N16, standard lap length is 800 mil. So go 0.92 plus 0.8 times 2. Ignore the spacing, and we'll just say, because there's 2 of these U-bars, we'll just make that 2. We'll get the total length of bars, which is going to be 5 meters for those 2 U connections, and that gives us that weight. And then the last thing we have to factor in is that as well, that those 2 meshes are top and bottom. So if we actually, the best way to do that is just to copy these, and we'll call that top layer, and we'll call that bottom layer. And then if you just copy these like that, and it factors in the top and the bottom, which gives us the total weight of the steel reinforcement of 0.1 tons, so 100 kilograms. Okay, so that's the steel reinforcement takeoff method. I know that was relatively long and rambly, but it's actually really hard to talk and do it at the same time. So I struggled with that. And I know I missed the starter bars, so you don't have to point that out. But that is the general process for how you do it. Adjust it for whatever slab you're choosing to do it. And remember the lap lengths, if the standard bar length is shorter than the length of the slab. Okay, so the next method is the ratio method, which is quicker, easier, and faster, but again, less accurate. So this is where you apply standard steel weights per meter cubed of concrete to different types of structures, and it's based on industry benchmarks, past projects, or typical from current project data. It's not as accurate as a full takeoff, but it is quicker and easier. So what are standard ratios you can use? Well, for different types of structures, you'll have different quantities of steel reinforcement per meter cubed of concrete. Footings would be something like 120 kilograms per meter cubed. Slabs on ground, the same. Suspended slabs, you'll have more steel because they need to be stronger. You'll have more like 150 kilograms. Same with beams, might be 180 kilograms. Columns would be 250 kilograms per meter cubed, and retaining walls would be 200 kilograms per meter cubed. You can then take these ratios and apply them to the volume of concrete. So how do you do this? You take the overall volume of the structure, you determine the type of structure, you choose an appropriate ratio, and then you multiply it. For example, if you are using the ratio 120 kilograms per meter cubed, which might be a slab on ground, and your slab contains 100 meters cubed of concrete, you can estimate that you'll require 12 tons of steel reinforcement. So now I'll do a super quick example to show you the exact same method on that same slab we just calculated before. And I'll also check the accurate calculation we did from the manual method and look at how the two line up. Okay, so for this slab, we'll calculate the volume. So it's 2.45 times 0.92. And I actually couldn't see this, but I'm assuming it's 200 mil thick. So we'll say 0.2. Why is that minus? So we're going to say it's 0.45 meters cubed. It's a slab. So the ratio we're going to use is 0.12. So 120 kilograms per meter cubed, or 0.12 tons. So steel will be that times that. So you get 0.05 tons of steel in that slab. How does that compare to this one? Well, this one gave us 0.1. So it's almost out by a factor of 50%. You can see this one is much lower. This one is much higher. Obviously, this is going to be a lot more accurate because it's factoring in the actual calculations. So if we did that same, so if we reverse engineered this, we'd get, to get kilograms per meter cubed, go that divided by that, and you can see it's more like 240 kilograms per meter cubed when we use the ratio 0.12. So there's actually a lot of steel in this slab. Okay, so let's finish off with some common mistakes people make in steel reinforcement takeoffs. In addition to the two I've already done in this video, which is using the wrong ratio when using the ratio method and not factoring in starter bars when I did the manual method. The first one is, which I've mentioned a couple of times, is missing the lap lengths. Remember, if your prefabricated bars are shorter than the length of the slabs, you have to factor in overlaps between the bars. Flaps are common in slabs, beams, and walls. The rule of thumb is 40 to 50 times the bar diameter, which will end up being quite a large percentage of the overall length. And again, I made this mistake missing the starter bars. So starter bars are used for walls, columns, or wherever you've got construction joints. They're shown in section and plan views, and they're easy to miss when you have multiple concrete pours. Now, something that I've seen quite a few people do is they don't understand what 200 mil spacing means. It means that from the edge of the slab, so from where you have the cover on the slab, you have 200 mil spacing. So if you simply take the width of the slab and you say, well, it's a 1 meter slab and I've got 200 mil spacing, that means I need 5 bars. That's incorrect. It should be 6 bars because you start at the edge of the slab and you'll finish at the edge of the slab. So it'll actually be 6 bars you need across the length of the slab. And the final one, which is more confusion, and this is genuinely difficult to do. When you get a picture of a slab that ties into another slab or a wall and there's 3 different section views, it is so easy to miss counting things or to double count them. So the way I'd say to do that is you just have to be really methodical with how you work through it. And finally, when you're doing steel reinforcement takeoffs, always apply a waste factor. I typically use 5%, and this accounts for areas, cutting, bending, or wastage of the bars. And not including it will ensure that you're always slightly underestimating quantities, because this is a true cost you need to incur. You'll always have some sort of wastage when you're cutting off bars that are too long, and so on and so forth. So always make sure you include a waist length. Okay, so I hope that helps. I'm sorry I was a bit rambly when I was doing the takeoff. It is surprisingly hard to talk and do that at the same time. Hope you enjoyed, hope you found it useful. If you want to learn more about construction estimating, take your skills to the next level, then watch this video next.